Have you ever wondered why you feel a push when you dive deep into a pool? Or why a balloon inflates when you blow air into it? This push is due to pressure. Simply put, pressure is the force applied over a certain area. Imagine poking a pin on a balloon. A small force applied to the tiny pin's point can easily burst the balloon. This is because the force is concentrated on a very small area, creating high pressure. Pressure is a fundamental concept in physics. It's all around us, even though we don't always see it. We can calculate pressure using a simple formula. Pressure, P, equals force, F, divided by area, A, or P equals F divided by A. This means that the smaller the area the force is applied to, the higher the pressure. Think about walking on snow. If you wear snowshoes, you are less likely to sink because your weight is distributed over a larger area, reducing the pressure on the snow. But how do we measure pressure? Scientists use a unit called Pascal to measure pressure. 1 Pascal is equal to 1 Newton of force applied over 1 square meter of area. That might sound complicated, but think of it this way. 1 Pascal is about the pressure exerted by a dollar bill resting on a table. Other units of pressure are also used, like atmospheres and millimeters of mercury. These units are often used in specific fields like meteorology and medicine. We'll learn more about these different units and their applications later. For now, just remember that pressure is a measure of force spread over an area, and it's everywhere. We live at the bottom of a giant ocean of air called the atmosphere. Just like water in a swimming pool, air has weight, and this weight presses down on everything on Earth. This pressure, exerted by the weight of the atmosphere, is called atmospheric pressure. We don't feel the weight of the atmosphere crushing us because our bodies have evolved to live with it. The air inside our lungs, for example, pushes outwards with the same pressure as the atmosphere pushing inwards, creating a balance. Atmospheric pressure is not the same everywhere. It changes with altitude. The higher you go, like climbing a mountain, the thinner the air gets, and the lower the atmospheric pressure. This is why airplanes need pressurized cabins to maintain a comfortable environment for passengers at high altitudes. An instrument called a barometer is used to measure atmospheric pressure. The most common type of barometer is the mercury barometer, invented by Evangelista Torricelli in the 17th century. It consists of a glass tube filled with mercury, inverted into a dish of mercury. The height of the mercury column in the tube is a measure of the atmospheric pressure. Atmospheric pressure is an important factor in weather forecasting. Changes in atmospheric pressure can signal changes in weather patterns. Low pressure often brings cloudy skies and rain, while high pressure usually means clear skies and sunny weather. Imagine diving deeper and deeper into the ocean. As you descend, you feel an increasing pressure on your eardrums. This is hydrostatic pressure, the pressure exerted by a fluid at a given depth. Just like the atmosphere, water has weight, and this weight exerts pressure on everything submerged in it. Hydrostatic pressure increases with depth. The deeper you go, the more water is above you, and the greater the weight pressing down. This is why deep-sea divers need specialized equipment to withstand the immense pressure at those depths. Submarines, too, are built with strong hulls to withstand the crushing pressure of the deep ocean. One of the fundamental principles governing hydrostatic pressure is Pascal's law. This law, named after the French scientist Blaise Pascal, states that pressure applied to a confined fluid is transmitted equally in all directions. This principle has numerous applications, from hydraulic brakes in cars to hydraulic lifts used to raise heavy objects. Another interesting concept related to hydrostatic pressure is buoyancy. Buoyancy is the upward force exerted by a fluid that opposes the weight of an immersed object. This force determines whether an object will sink or float. If the buoyant force is greater than the object's weight, the object will float. If the object's weight is greater, it will sink. Section 4. Measuring pressure. Tools and techniques. Understanding and measuring pressure is crucial in many aspects of our lives, from checking tire pressure to monitoring blood pressure. Over the centuries, scientists and engineers have developed various tools and techniques to measure pressure accurately. One of the earliest and most well-known pressure measuring devices is the barometer, which we discussed earlier in the context of atmospheric pressure. Barometers use a liquid column, typically mercury, to balance and measure the weight of the atmosphere. Another commonly used device is the manometer. A manometer measures pressure differences using a U-shaped tube filled with a liquid, usually mercury or water. By observing the difference in liquid levels in the two arms of the U-tube, one can determine the pressure difference between 2 points. For measuring pressure in industrial settings, pressure gauges are widely used. These gauges typically use a Bourdon tube, a C-shaped tube that straightens as pressure inside it increases. The movement of the tube's free end is then amplified and displayed on a dial, providing a pressure reading. Modern pressure measurement techniques often involve electronic sensors that convert pressure into an electrical signal. These sensors offer high accuracy, fast response times, and the ability to interface with computers for data logging and analysis. Accurate pressure measurement is essential in many fields, including healthcare, manufacturing, and scientific research. Understanding the principles of pressure measurement and the tools used is crucial for ensuring reliable and meaningful results. Pascal's law and its applications. Blaise Pascal, a French mathematician, made groundbreaking contributions to our understanding of pressure. Pascal's law states that pressure applied to a confined fluid is transmitted undiminished to every point of the fluid and to the walls of the container. This principle has far-reaching applications in our daily lives and various industries. Hydraulic systems are a prime example. They use an incompressible fluid to transmit force and motion. A simple system consists of 2 pistons connected by a filled tube. Applying force to the smaller piston transmits pressure through the fluid to the larger piston. The larger piston experiences a greater force, proportional to its area. Applications include hydraulic brakes, lifts, and presses. Pascal's law profoundly impacts technology and our daily lives. From cars to construction, Pascal's law makes our lives easier and more efficient.